El curso se va a dar en inglés. Voy a empezar a hablar inglés. Good afternoon, everybody. Welcome to this course. Neutron diffraction for advanced engineering materials. Our instructor is Professor Mohamed Naeem. He is coming from the University of Hong Kong, and we are giving him the welcome to Mexico City and to the National University of Mexico. Let me read a short bio of Professor Mohamed Naeem. His background includes a bachelor's degree in Metallurgical and Materials Engineering, a master's degree in Materials Engineering, and a PhD in Materials Physics. He has been a full-time teaching faculty of Metallurgy and Materials Engineering related subjects in the Pakistan Institute of Engineering and Applied Sciences. He is currently a postdoctoral researcher at the Department of Physics of the City University of Hong Kong, and co-supervisor of 2 PhD and 5 undergraduate students in Hong Kong and Mexico. Really, in Mexico? Good. The focus of his research is on the deformation behavior of multi-component alloys under extreme thermal conditions. He employs neutron scattering for the in situ structural calculation. Been awarded the Young Research Fellowship by the Asia and Oceania Neutron Scattering Association, as well as the prestigious Marie Curie European Fellowship. He has been visiting various international large-scale neutron scattering facilities, including the support for designing and execution of neutron diffraction experiments. He also received the award of Best Paper on Materials from the Hong Kong Institution of Engineers in 2020. His work has been published in well-reputed journals such as Design Advances, Acta Materiala, Scripta Materiala, Applied Physics Letters, and so on. He will be chair of the Gordon Research Seminar on Structural Nanomaterials in Switzerland in 2024, to which all of you are cordially invited. Before giving the word to Professor
Hello, thank you so much for joining to this course and this seminar. I just want to give you some instructions, and thank you so much to Dr. Naeem to be here with us. So I just want to remind you that we will start today with the course from 3 to 5 p.m., but the course will continue tomorrow and also on Thursday, okay? And today, after the course from 5 to 6 p.m., we will have a seminar also by Dr. Mohamed Naeem. And this seminar will be about high entropy alloys, which I think you know is a very novel topic in metallurgy, and it can be a new research line for us at this department. So I think it's highly worthy if you can stay at the seminar of today at 5 p.m. And today the course, because of this seminar, will finish a little bit like before time. We will finish at about 4:30. And Wednesday and Thursday we will have a break, and a coffee break. We will share some coffee and some biscuits from 4 to 4 and 10, okay? So this is the dynamics, and hope that you will enjoy a lot. Thanks for joining. Please, Dr. Naeem.
Thank you very much. I'm very happy to be here, and this is my first time in Mexico. So I was very excited to see new places, and hopefully I can meet people as well. So how it's gonna work out? So because it's divided into 3 days, and so today I will just give very fundamental concepts about neutron scattering, and then tomorrow maybe I can share some applications of this technique with you, which will be mainly about neutron diffraction, because neutron scattering have number of techniques which we can apply. And on the third day, maybe I can focus on a different package about data analysis. So usually I speak very, very fast, but I will try to speak a bit slowly, and I would love if we can interact, like you can participate. You can stop me anytime to ask any questions or for any comments or whatever you think appropriate. And you can also ask questions in Spanish. Dr. Liliana will of course translate that, because I don't speak any Spanish at all. But of course, if like you will say in English, then of course I'll be there and somebody, don't worry, like you can also ask in Spanish and she will totally translate and I will be able to answer that. Okay, so I normally don't put table of contents because I usually go like that, really like okay, because in that way we can like cover more dynamically. As I said, like please feel free to ask anything or stop me at any time. Okay, so we can start. So as you know that my background in metallurgy, and I assume that most of people here are also metallurgy. So I will be mostly talking about alloys, at least like in second and third part of this course. But today is mainly about neutron scattering and neutron cells. So there might be a lot of repetitions, so I will be saying the same thing a number of times, just like get my point across. Okay, so I think we are here like why science they can find it right? Okay, but then I don't have to do this, then I can so oh, perfect. Then I can come back. Okay. Okay. So because we have been studying engineering for, from few years to many years. So I think we all know why we need in-service analysis for engineering materials. And just to give you some examples. So this is one of the image, because we can have different kind of services, not just in alloys, but also in this pitch, which involves some steel, but also it's complete. So this is the collapse of Twin Cities Tower in Minneapolis state in 2007. And it killed, it was totally unexpected, and it killed a number of people at that time. Then this is a train crash in Germany, and it killed almost 100 people and injuring almost 200 people. Because of fatigue, I think all of us are aware of fatigue. So because of fatigue crack, this train collapsed, and it was also unexpected. It was single fatigue crack. Then this is another example of China airline, which collapsed I think near Taiwan, and it killed all the people, 200 plus people on board. So these are different kind of examples. They involve very different kind of materials. But then the accidents happen, then they can be very deadly. So we have to, for that reason, we have to have these kind of analysis, and we have to do preventive maintenance to make sure that no such thing happen. So of course, like we want to have these kind of analysis for lasting performance, so that we can make repair and its longevity can be extended. Second, of course, cost, because if it collapses, then it will involve a lot of expenses to clean that up and to rebuild it. And third, of course, the most important one is public safety, because human life is the most precious thing. And you can see from these examples that through these accidents, how many people were killed and injured and paralyzed for their whole lives. Okay. Now, the second thing is about, of course, we need analysis, but sometimes we cannot just, we do experiments in our labs. So we usually cut a sample and we take it to, say, a tensile testing machine, or we take it to XRD, or we take it to TEM or SEM, and we put it over there to observe which kind of structure or which kind of things it have. But that's not always the case. Sometimes we have to do inspection while the thing is in service. So that is very important, which we call real-time analysis. So that's the reason like we need it. So because all of us here are metallurgists, so the best example I can give you, so I will be mainly talking about alloys, as I said. So I can give you one example of, for example, tripped steel, which is transformation-induced plasticity steel. And we know when we deform it, it can undergo phase transformation from arsenide to martensite as a result of this stress-induced or deformation-induced mechanism. It changes crystal structure. We know, but when we do test, and then we take it out, and then we go for XRD or we go for, say, TM to look at it to see which kind of structure it formed. But we cannot know when it really started. So in real time, we can really see when it started. Or for example, we are heating up something, and we want to know like which kind of changes are happening with regard to crystal structure. Second example is again from a metallurgical point of view. We always work with the different kind of heat treatments and mechanical processing, which is main component for metallurgical and steel industry or any kind of metal industry. And so we want to know which kind of changes are happening, say during deformation, during cooling, during heating, and so on. So if we have real-time observation, then we can really pinpoint and we can manipulate in a better way to achieve better properties, and maybe also we can reduce some cost. Third example, this is my own topic, so I always love to talk about high entropy alloys, which I've been working for some time. And they are a bit unique, and I will talk about them in the around 5 p.m. Which will be about high entropy alloys. So one of the most magnificent thing about these alloys is that their ductility increases at low temperature, because usually we see that ductility decreases when we go to cryogenic temperature. And sometimes they become totally brittle, sometimes they are not brittle, but their ductility decreases. But for these alloys, usually ductility increases at cryogenic temperature. And I will of course discuss in detail in the afternoon. Then another example is about shale memory alloys, which can retain their shape as a result of different kind of transformation changes. As a result of say stress, as a result of thermal treatment, and so on. So that we can also observe in real time. And you know, as you know, shale memory alloys are a very high elastic limit. For usual alloys like steel, the elastic limit is less than 0.2%. For shale memory alloys, the elastic limit can be 4% or even more than that. So these are some of the examples of things which we can do in real time. And ultimately, of course, I have to come to neutrons. Okay. So now we can come to another point about which kind of analysis we do. And everyone can hear me clearly, right? Okay, perfect. Okay, I will slow down a bit more, just okay. So for example, automobile industry is one of the most important industry in the world, and it involves very different kind of alloys, from composite to aluminum to titanium to steel. So when we look at its structure, so it can have multi-scale. So when we look at one workpiece, we can go EST, which is we can look at the structure at micrometer scale, in which we can see grains and so on. Then maybe we can within grains make distributions, right? And that we can see by GM at nanometer scale. But at the end of it all is lattice, which determine almost everything at which kind of structure. And that is what we're talking about. So lattice is usually around nanometer level scale, maybe like angstrom scale when we talk about atomic. And what you want to do, but never mind. What you want to see is studying practice. You want to see how these actions are used. And then we can divide this up.
he was really good. I think that characterization of the structure. So he was basically looking at different applications. And was how you can see that. It actually very short, very small, so I can just very direct. Start from you can start from the 60 on reactor, nucleic reactor. Because when they were working on this, they were on source of and that was nucleic reactor. Because the reactor is neutrons. So this is neutron coming from and we actually have monochrome reactor. The purpose of this is and I think you know one of the methods to kind of select particular neutron. And then this select here, and then this detector here is detection of these neutrons. And this is basically what it was elastic scattering. Then our school was working on inelastic scattering. Concerned about dynamics of energy change. Then neutrons in electric matter, they certain parts of energy and how that energy changes. And that is very useful for studying the say photons or electrons. So that was his and because neutrons when they are released they can have energy and that energy is related to energy. So what we really want for neutrons to have trouble energy. Because if they have high energy, then they will be not able to detect energy. So if they are that's how okay, now this is very fun. I think I don't know this. Okay, I think I can ask one question. Okay, what is special about Neutron? Why special? Why they can yes. That's the main point. Because electrons have effective the kind of communication. They do not be able to detect electrons that they come from. Okay, so what's the point that like we say use electron diffraction like that has like that one completely but is that very important. So you do not how So for X-rays, it's scattering also is great practice. So heavier than the chromium manganese, they are very close. So you have to another thing is about isotopes, because when we have interaction with electrons, then nucleus and isotopes comes from excessive number of electrons. So that's why we can also distinguish isotopes. We can actually fraction is very common. But for neutrons, hydrogen, which is very, very light, that's really good to study with the neutrons. So a lot of people who work with proteins and biological substances, which can be very good for them, similar to polymer people, it can be very, very useful for them to have neutrons or neutrons. And you can see it's not linear. Some of them have that, for example, you can see hydrogen, and then you can also see deuterium over here. So you can distinguish between isotopes, as I was saying, because it interacts with nucleus. And also it can distinguish between neighboring elements, because it all have to do with, they have very different cross section, it does not depend on that number. So for example, if you have chromium, manganese side by side, you cannot study with neutrons, will come to those. So because as I already mentioned that their scattering length or scattering cross section is independent of atomic number, so we will have a different kind of interaction. Then they are more sensitive, as you have seen over here. They have larger scattering cross section for very light elements. And then as I mentioned about isotopic sensitivity, that they can distinguish between different isotopes. Say for example, hydrogen, deuterium, and tritium. Isotopes of hydrogen, they have very different scattering cross section. And this is also very helpful. For example, if you want to, there is a very broad field in neutron scattering where people do isotope substitution, that you can substitute one isotope for another one in one part of say protein, so that we can have its interaction different from the other one. So it's very useful. And then of course that's what I suggested, that you can use contrast variation by isotope substitution. Okay, so advantages. So one is its mass and its moment transfer is around interatomic spacing. So that can give us what we get from diffraction. Then it's zero charge, as we were talking about, so it's highly penetrating because it will not have any field acting on it. So for that you can really, because in metallurgy most of the time we work with the bulk materials. It's not like we will be dealing with like really tiny things. For example, with the X-rays we really look at just surface, just micron level. But if we really want to look, we have like 3 millimeter thick sample, we really cannot see beneath like few micron. Same with the electron diffraction. Actually, electron diffraction sample making is a huge, I mean, it takes a lot of labor to really make a good electron microscopy sample. But in this case, we can really probe bulk behavior. And so we can like cover more areas, so we can benefit from large samples. And we can also use extreme environments. For example, I will talk about it in seminar as well, that we work at very high or very low temperature as well. And we can have in situ, say, thermomechanical treatment as well. We can apply magnetic field, we can apply pressure to get different kind of real-time information. Then because of magnetic dipole moment, we can interact with unpaired electrons, and we can study magnetic structure and spin excitations. But everything has some disadvantages. If you have like some plus, you have to sacrifice on something. I mean, if like you have
one thing which can answer all of your problems, and I think that would be amazing, but that does not exist. So that's why when we do experiments, we combine different kind of characterization, because one technique can give us one kind of aspect and another can cover another thing. So one of the disadvantage of neutrons is they are very, very, very slow. So it takes very, very long time to measure pattern. With X-ray, you can like measure, like especially if you go to synchrotron, you can measure like within second it's done. But here, like you really have to wait for some time, depending on which kind of materials and how thick it is. These are two, and composition. Okay, composition, cover material. So which kind of elements it have because of scattering cross section, and how big it is. I think these are the two main points which we have to remember. So it have a low intensity or resolution, so we have to use large samples, and it can also like we can have statistical noise as well. When you have high penetrating power, then you can also have issue with background, because then you really have to control that as well. Again, you have to have larger samples so that you can have good statistics to achieve that. And third one, as I was saying, that for neutrons experiments, they are good for some way for nuclear reactor applications. So some of these, boron, cadmium, and gadolinium, for example, they have a very large absorption cross section. We need high scattering cross section, but we should have low absorption cross section, because if material absorb neutrons, then we won't get anything out of it, right? It's gone. So boron is called neutron poison, and it's used in nuclear reactors to shut down, nuclear fission reactions and to stop, whenever we have to shut down reactors. So boron rods are usually used. Similarly, cadmium windows are made in these facilities so that no neutrons will come out. So if your material have any of these, especially boron, even if in tiny amounts, say even like in fraction of percentage, it can be difficult to really study them. So you have to, like, before you go for like your experiment, you have to decide like it is really good for using neutron for these kind of samples. Okay, and of course, again, like with every like cone, with every pose you have a cone, and here cone for being neutral it is really hard to manipulate. You cannot really, its acceleration is very, very difficult thing. You need like huge magnets to really, drive neutrons and to bring it to the sample. And the similar detection is also another issue, because it's like neutral, so you have to use very special kind of detectors and very, very expensive detectors. So this is the reason that there are very, very few neutron facilities around the world, because it's very, very cost intensive. Okay, so within neutron, as I was saying, that neutron diffraction is one kind of neutron scattering technique, which I will be discussing most of the time. And as everyone is familiar with the X-ray diffraction, so I think everyone will understand that what happens in neutron diffraction. It just follow Bragg's law, and we put our material in front of the neutron beam, similar as we do in XRD, and ultimately we get we can see crystal structure, we can see lattice spacing, and so on. And it's in this case, its wavelength is around 1 angstrom. So this is for crystalline materials, but we can also do with amorphous, by the way. Before working on high entropy alloys, I have been working on something called bulk metallic glasses. They are alloys, as you can see, bulk metallic. So they are metals, but they have crystalline. They don't have crystalline structure. They are amorphous. That was a very interesting field a few years ago, but now I think many people. So in that you can also have some kind of response from, especially if you study with neutrons. So you can get some peaks, not like sharp peaks, but we call it diffuse scattering. So you can get those kind of peaks, and you can still like differentiate between different kind of amorphous materials and under different kind of conditions. You can have a different, we call it pair distribution function analysis. to get this kind of information. If you are interested, I will be more than happy to talk about that, but I will not discuss over here. Okay. Diffraction is one of the technique which is most widely used, but there are also other techniques which have specific functions. One of them is small angle scattering. So with small angle scattering, we usually do large scale structure studies, because with this diffraction we will look at atomic structure, right? We'll be looking at lattice spacing, but with the small angle scattering we'll be looking at particles within matrix. For example, in colloidal solution we can have embedded particles, so we can, or for example with superalloys, we can have matrix and then we have some precipitates in them, right? So we can also study them with small angle scattering. Is it okay? Okay, I hope so. Okay, so with that you can have like around the order of 10 power -7, like hundreds of nanometer structure you can see. So it's basically for particle size, particle shape analysis, because we cannot really, of course you can do with the electron diffraction as well, but sometimes the size is so big you can really not get statistical average, because you'll be looking at really tiny region. So this can be very helpful for looking at bulk materials. And then there is deflectometry, which we basically use for profile analysis for concentrations and surface profile. So it leads to composition. For example, when you have difficulty with the isotopes or anything like that, then it can be very helpful for getting a composition analysis. And the last one, at least over here, is inelastic scattering, which is spectroscopy, which is basically we deal with energy change, what we call dynamics. So one thing missing over here is what we call radiography, which is also used for X-ray, which is very popular. I mean, X-ray radiography, for example, if we have something happen with our bone, so we go to just radiologist and we get this X-ray. So same neutrons can be used, but with neutrons we can have some advantages. I will show some examples at the end about radiography with neutrons, because they are very interesting. Okay, so now I will talk about, because I mentioned that today I will be just talking about basics of neutron scattering, about neutrons are, what they can do, their basic properties, how to obtain them, and what are the main facilities where you can do neutron scattering experiments. So I will be talking about really good things about neutrons for today. Tomorrow I can focus on some data analysis maybe, and then on the last day I can show some examples, or maybe vice versa, depending on how I get feedback today. Okay, everything good so far? Everyone awake? Okay, excellent. Okay, so we can have two kind of sources for neutrons. One is, of course, the first way, like really neutron scattering. When really a neutron experiment started, that was with nuclear reactors. And the second one is spallation sources. So it started with reactors, but now reactors are going out of business, and now it's more moving towards spallation source. Maybe because they need less regulations compared to a reactor. So nuclear reactors, I think even like high school, you guys might have studied about what nuclear fission is, and how a uranium, for example, uranium-235 split, when you bombard neutrons on uranium-235, it's split into daughter products, and then it releases some extra neutrons as well as some other radiations. And so on the average, okay, I think I should have a schematic over here. Okay, so you have a neutron which interact with say uranium-235 element. It split into two, so we have these fission products, and then we have 1, 2, 3 extra neutrons. On the average, we have 3 extra neutrons. I mean, not extra, but 3 neutrons as a reaction, as one reaction of a fission reaction. So then you can use another neutron to like continue this reaction. You can have these 2 extra neutrons which you can use for experiments, because you have to continue chain reaction for reactor to work.
for it to be in kind of chain reaction. And this is one of the example for which where they use reactor source for neutron scattering experiment. This is called Fermi 2. This is in Munich, Germany. And you can see this is a reactor core, and there are fuel assemblies inside it. And this, I don't know if you know about this color. This is because of Brahms-Starling radiation. And they use, of course, like some coolant to cool it down. And there might be some detailing. Oh yeah, so this is the schematic, like that's how reactor works. So you have kind of a calendiar kind of a container, and then you have a fuel assembly over here. You have some coolant, you have some moderator because you want to decrease energy of neutrons. For that we use moderator, so that we can have more thermal neutrons for interaction with our material which we want to study. And as I was saying that there are control rods which basically control reactor, I mean, as the name says, and they are usually made of boron, because as I was saying that boron is really poison. It just eat all the neutrons and then reaction will stop. So if you lower these rods inside, so the chain reaction will stop. But if you lift them up, then you can increase the activity and activate, and then you can have higher power. So that's how the power is manipulated. Moderator also do the similar kind of function, because you have to have thermal neutrons to continue the reaction. So you can see there is this window over here, which is made usually to get neutron beam to the samples or for the experiments. Okay, so this is a continuous process, so it will continue. Like your reactor will be operating, and you will have continuous supply of neutrons. But per fission, I said like you will have 2 extra neutrons. But here it says 1 neutrons per fission you will get. Because the reason is there will be some neutrons which will be absorbed by, because you have this calendia, you have moderator, you have coolant, you have some other materials as well. So some of our neutron absorbers. So some neutrons will be lost over there. So on the average, you will have 1 neutron which will be available for experiments which you want to conduct. So this is per fission reaction, but this is a continuous supply of neutrons. Other example is spallation. Spallation we don't use. So as I think I mentioned, is uses fissile material, which can produce neutrons. For example, uranium-235 is the best example. But if you don't use fissile material, or you don't have access to that, or like regulation, like because it can be also used for weapons. So this is now the more like popular source of neutrons, which is spallation. In this, what happens is a very heavy particle, usually helium nuclei or something like that. They are excited, or they are bombarded on heavy metal target. Usually it's mercury or tungsten, something like that. Different sources use different kind of target elements. That's what we call target element. So these protons, they are excited at a very, very high velocity or very, very high energy of more than 1 giga-electron volt. And they they just hit this heavy atom. And you know why heavy atom? Can anyone tell like why they use heavy atom? Why not like something else? Anyone? Okay. Because when we increase atomic number, when we go into heavy elements, they have more neutrons than protons, right? That's how it was. Like initially, like you have less neutrons, but as you go to larger, higher, very, very heavy element, they have more neutron. So when we want to get neutron out of them, so I think they are the best material. But you cannot use all of those, because some of them are very, very stable, or some of them are not suitable for these kind of experiments. So there are some options which you can use. As I mentioned, you can have mercury, or you can have tungsten maybe. So one source, I think in one of the sources at Oak Ridge National Lab, they are using in US, they are using, I think, tungsten, while one of the another source in Japan called J Park, they are using mercury. So depending on which kind of technology they are good at, their industry, I think they usually go for that. Because you have to cool it down because it will produce really huge amount of energy. Same, I forgot to mention that even here, like it says 1 neutron per fission will get, but per fission it will release 200 megawatt, MeV, mega electron volt of energy per reaction. So you have to cool it down. So that's why you will usually see these kind of facility, they are built closer to oceans or closer to rivers so that they can continue supply for cooling, also away from population, at least for nuclear reactors. Okay. Right. So it will be bombarded on this at a very high velocity, and then there will be kind of cascade of these reaction, and you will have kind of a evaporation, kind of like really a lot of like neutrons will be like coming out, but also a lot of other kind of radiation like alpha particles and beta and gamma and so on. So in simple, so this is the main difference between these two sources. So here you have a neutron. It reacts with fissile material, and it split into two here, and we get 3 neutrons per reaction. So one to continue the next reaction, one for experiment, and the third one may be lost somewhere. It can be absorbed. So it is a continuous supply of neutrons, but it will only be available as long as the reactor is working. But the output is very low, like 1 neutron per fission reaction. The spallation we have proton at a very high speed, more than 1 GeV energy. It collide with the heavy element, mercury, tungsten, and then we get kind of lot of neutrons with different energy, and also we get some other kind of particles like neutrons and protons and so on, and alpha particles as well. And this reaction like happen in the material, like it depends on what is the frequency of facility. Facility is neutron scattering facility. If like it's operating at 25 hertz, but in this case it's kind of like pulses. So that's why they also call pulsed neutron sources. So you have pulse of like neutrons for a moment, and then it will stop, and then next cascade will happen, and you will have next pulse, and so on. So in this case, you will have a lot of neutrons instantaneously, but it will be like in pulses, like one pulse, one. But in this case, you will have neutrons of all kinds of energies. In nuclear reactor, you will get just thermal neutrons, but in this case, you can get with all kind of a range of energies between wavelengths. So when we talk about neutron diffraction, usually, which if we do it by say pulse neutron sources, we usually don't talk about what is the wavelength of our source. For example, for XRD, which we usually use, if we have copper K alpha target, what is the wavelength for that? Does anyone remember? Wavelength for copper K alpha, the source which we use in our labs. Okay. Everyone's still awake? Okay, it's 1.54 angstrom. That's the wavelength which copper K alpha have, which we use in our labs. But when we go to say Spolation source, it will have all kind of wavelengths. So I will show you facility later that how it looks like. So you can take advantage of that. So you can build it for different purposes. You can have very high intensity sometime, and you can sometimes have very high resolution, depending on what you want to study. So they built specialized beam lines. So we call them beam lines, by the way, like each like line which is coming out of this source, and it have so it is built for specific kind of materials which we study, a specific kind of mechanism which we want to study. For example, elastic scattering, elastic reflectometry, radiography, and so on. So it depends. So we can like make use of that. Okay. Moving on. So these are some of the sources in the world. I don't think like every single source is there, but major one are there. There might be like some really, really tiny somewhere, but I think they are not here. So some of them are yellow and some of them are, I don't know, which color is this? Is it brown? Okay, just call it brown. Red? Okay, red. Okay. Okay. Some are red, some are yellow. So there are two different kind of sources. So yellow one are with which have a new reactor source. For example, this is very old one in Chalk River in Canada. So this was reactor source. Similarly, at NIST, National Institute of Science and Technology in US, they have this is reactor based. Similarly, this high flux isotope reactor at Oak Ridge, this is reactor based. While spallation neutron source, as its name also says, SNS is spallation neutron source. That is also at Oak Ridge National Lab. That is pulse based or spallation based. This is I forgot where. I think it was in Chicago. This one, and then in UK they have one. It's called ISIS. It's a different kind of ISIS than the one which we usually hear about. But they named it before that happened. So because you know what is ISIS, by the way? I mean this ISIS, not like the other ISIS. ISIS was it is a I think Greek god. It's one of the Greek goddess, actually, not god, goddess. So they named after like one of the god. But somehow, like later on, it turned out to be a bad decision. But anyway, they still call it ISIS. So this is also pulse space. Then there are some in Europe. So this is also in Europe, but these are like so in Germany they have these two. For me, two I already shown you, which is nuclear reactor based. Then one in this is in I think also Munich. Then this is in Budapest Neutron Center in Hungary. Then these two are in France. They both are reactor based. And these two are in Switzerland, SINC and ESS, European Spallation Source. This is like ESS is still not started. They have been trying to, it have been delayed for at least like 10, 15 years. So as name implies, so it's contributed by like at least 30 countries. So that's why it's so slow and like so many, administrations are involved. Then there are some in Asia. So I usually, most of the work which I have done at JPARC, which is in Japan. It's called Japan Proton Accelerator Research Complex. It's also a pulse based spallation neutron source. They also have a very old one. It's called GRR3. It was reactor based, but it's just now like a very limited use. One in Korea called KERI, Korea Atomic Energy Research Reactor, which is also now going out of operation very soon. And these two are in China. This was very small, but now they build a very huge one, CSNS, called China Spallation Neutron Source. And at the moment, the highest power source is this one, JPARC, Japan Proton Accelerator Research Complex. It was expected that ESS will overcome this limit, but first they have to start it. So let's see when that happens. And the CSNS in China, they are also trying to increase power, and soon like maybe they will be reaching at maybe same level as Japan. And there is one in Australia called ANSTO, Australia Nuclear Scattering Technology Organization. That is also reactor based. So they have 60 megawatt reactor. Actually, the very first experiments which I did was over there. They have 60 megawatt reactor called Opal, and it was built new. I mean, like the newest reactor based source in the world is this one, which was built in 2006, like almost 17 years ago. But remaining all new, whichever are built are mostly spallation source based, because they don't need fissile material, so you can really like avoid some regulations regarding regulation wise, security wise. Second, also because of reactor accident. I mean, like there have been very few reactor accidents, but we cannot afford nuclear accidents. The latest one, I think maybe like you remember, like the one was in Japan. That was not over here. That was at a power plant, Fukushima. So it did not, I mean, the casualty rate was almost nil, but the contamination which it is caused to say C and to C live, and that was huge. So that's why, like after that, you know, like in Europe, like they started decommissioning their nuclear reactors. But so that's the reason they are moving towards spallation sources, because it is, and also it is more safe. You will not have those kind of accidents. Of course, you can have accident even like in our labs as well. Working with tensile machine, you can have accident. You can have like accident at home. But spallation sources are very, very, very safe when they are compared to nuclear reactors. I'm not saying that nuclear reactors that they don't do everything possible in their, but still, now like this is how the situation. All of these nuclear reactors, they are very old one. Okay, this is about flux. How much flux we can get out of nuclear reactor. So it started over here with Chadwick, with his. It was called. I think he was doing charcoal. I think this is similar, but this was built on Chadwick a charcoal pile experiment in 1932. So at that time, its flux was, you can see, touching 0. And then you can go up and you can see. So these were all kind of what we called research reactors, because there is difference between like research reactors and nuclear power reactors, and the third one is what we call now like scattering facilities. So these were just like, basically their purpose was to make, during this time, the sole focus was on weapon production, because this was during Second World War. During that time, everyone wanted to like, so usually most of them were in US, by the way. And here you can see which is still functioning, which was, now you can see this is very, very old HFIR, but it is still functional at Oak Ridge National Lab, high flux isotope reactor. So of course they have to upgrade it, but it is functional. Similarly, ILL in Grenoble in France, that's also working. That was built in 1970. So these were all like, so this line, that was reactor based. And you can see that here, their flux almost flattened. So there was a limit, like, so they could not increase flux. So that was like any new like technology they had, like any new reactor they were building, its flux was remain almost asymptotic. Then started spallation source based, and they actually started mostly in China and Japan. So at Tohoku University, so they had like small facilities over there. And now you can see it have really taken over. So now their flux is like at least 2-3 order magnitude of higher than reactor-based sources, right? Okay. This is what happened in scattering, which you know, I don't know I think I never met this guy, but everyone uses his this hand sky drawing. It is very interesting, I think. So what you do, you direct neutrons, you polarize them. Sorry, I have to drink some water. You can enjoy this drawing meanwhile. Okay. So polarizer to direct neutrons towards sample. So that's why you can see having this thing, and it's like pushing these mice towards cheese. I love cheese. So this is sample holder. So you have like sample holder, you have a sample on that. So these will pass through, because neutrons are, you know, like they can pass through the sample. Depending on which kind of material you are using, they can like pass up to easily 10-15 millimeter for steel, for example. Again, depending on what is beam power. But for some materials, for example, titanium, it may not be. You have to like make it thinner. It will be different thickness which it can pass through. Okay, so sorry. So then after they interact, so they will be scattered. So if they are absorbed, then we won't get anything out of that. They are gone. We'll not get, because we have to get ultimately diffraction pattern. That's what we'll be looking at, or maybe radiograph or something like that. But if we don't get, if they are absorbed, then they are gone. So ultimately they have to be counted by this counter, big bulldog. So once they will scatter, they will ultimately be counted over here. And so the main thing which you will hear a lot when I say like from me, like time of flight, we always use, especially for pulsed sources, we say time of flight. That's how we determine their structure. So time of flight is basically for neutrons, starting from here, reaching up to detector. That is the time which it takes. So for that, they can ultimately convert it to d-spacing, or what we call lattice spacing. So they have a detector and they have its configuration, and we know which kind of detector it is. And for that, you can convert. I will show you that maybe in second lecture or third lecture, second probably. Okay, so they are directed towards the sample. It's injected with sample. It are collected over here, and that's all. That's it. But that's also what we do in XRD as well. But in XRD, we don't have our moving, for XRD, we are moving detector. So detector are moved like this, right? To collect, for example, I think the lowest, it can start from 2 degree, but usually we don't go to that low degree, low angle. 2 theta of 2 degree to all the way maybe like 180 degree. But 180 again, no, maybe a bit less. But here we don't have to like move detector. Move detector is like covering, like, because these neutrons, they have different wavelength. They are not just coming from one wavelength. For XRD, we have single wavelength, but here we have multiple wavelength. So they will take different time to reach to detector. And after interaction, okay, I think I'm like getting ahead of myself, so I will show it later. Okay, so this is the simple principle, very, very simple. Okay, so this is the one example of Spolation source, which I would like to show because this is where I did most of my research. This is called J-Pod in Japan. And as you can see, so this is Pacific Ocean. And this is a tiny town in Japan called Tokai. It's in Ibaraki Prefecture, around 3 hours of drive from Tokyo. So town, again, like it have to be like away from population. So the most of the people who live there, they are mostly work there. So they are the workers. I mean, in this facility, it's a huge facility. They do different kind of, they have both neutron as well as muon facility as well. Excuse me. And usually like it's people like us who go there to do experiments. So it's like all of them, like either they're working there or they are just visiting there to do research. And so it's a huge facility, and it have a linear accelerator, which is 330 meter. And so the protons, they're accelerated over here. Its energy is 400 MeV. Then there are a circular ring where a circumference, you can see, they are accelerated at 3 giga-electron volt with these really giant magnets. They are accelerated to the next ring, which you can see over here. Here their energy is further increased to 30 joule. And finally, they are released for the target, and we get a cascade of neutrons. And along with that, you have neutrons, but you will also have different other kind of particles. And they have different other facilities which they can use those as well for other kind of research. For example, we are talking about materials research mainly. Or actually, materials is everywhere. Like it's not just steels, but also glass, also wood, every kind of materials, biological materials. But also they have, when they have these fundamental, other particles, they can use it for fundamental research. For example, I think you may also know about Higgs bosons. That was a big story, and Peter Higgs got his Nobel Prize, I think 60 years after his papers in 1960s about existence of these bosons, which now we call Higgs bosons, that research was carried out at LHC, at Large Hadron Collider, and they used these other particles to do that kind of research. So most of these facilities, they have those kind of research as well, which is we call like particle physics research or fundamental research. But most of the research, the neutrons which they use, that is mostly used for, they have a facility called Materials and Life Science Experimental Facility. And as I was saying, they can have different kind of beam lines. So this is the source in the center. I was telling you that this is Spolation source, right? And it should have a heavy target. So I did not put picture of it. Maybe next, tomorrow I can show it. So they have a huge target, and these protons, they come at, you can see 50 GeV energy, and they collide with, they have mercury right over there. They collide with it, and then we can get neutrons with different energy. And you can see there are different kind of lines going from center of this target. We call it target. You can see they are of different length. Some are like very close, some are far away, right? This one, for example, it is quite far. So it depends on which kind of properties we want to study, which kind of interaction which we want to pursue, elastic, inelastic, so on, and which kind of materials we want to look at. So you can find like, for example, this facility called Planet. Planet is just its name because they do high pressure research. So mostly it's the geological people who come there to really study, say, earth, magnum, and so on. But also we can study, say, iron, because that was also like made when the universe was, after Big Bang, like everything came into existence. So they do that kind of research at very, very high pressure. Then you can see, for example, this one, it's used for fundamental physics research. Then you can see, I don't know, some for spin, some powder diffractometer, some protein, so biological materials, protein single crystal. Sorry, for some for backscattering, some chopper, and I want to find small angle neutron scattering, which I was saying that you can use for particle colloidal kind of experiment. Then you can see reflectometry, single crystal diffraction, and here it is engineering materials diffractometer, this one. And the powder, which is usually used for texture studies, and so on. And also there is imaging, so you can also have neutron imaging. Everyone okay? Okay, I will take 10 more minutes, then we can stop, okay? Okay, so but I want to emphasize that when you hear about neutron diffraction even, it does not mean like you can take the same sample and you can go to this one place. Maybe you have to go to some specific. For example, if you to study, say, deformation experiment, that's what I usually do. Then you have to go to some specific instrument. If you want to study texture, I think then this will be maybe better. If you want to study, say, what happened like in situ deformation, then maybe engineering materials diffractometer is the answer. If you want to study, say, supralloys, but you want to look at nanoparticles in the supralloy, for example, gamma prime. So I think the best option could be, depending on you want to just look at that, then maybe this will be the answer. So you have the same source, but depending on which kind of properties and which kind of materials you have, you will decide, okay, this will be a best option for me. Otherwise, you cannot like always like, okay, if someone work on neutron diffraction, maybe like I work on one kind of neutron diffraction, but I may not know other diffraction. I mean, maybe I know about them just a little bit, but I cannot be expert in that because it can be a very different field. Okay, so usually, but here, like from metallurgy point of view, of course, there are a number of instrument. Usually they call them instrument, by the way, or beam line, which we use them interchangeably. So usually for us people working in metallurgy, it could be small angle neutron scattering if we are working with the different kind of, say, supralloys. And then it can be, for example, high engineering materials diffractometer. which I work with. Actually, exclusively I work with this beamline. And also can be, if you want to look at texture, then it can be powder, this iMateria powder diffractometer. Their names are just people who designed them, they named them how they wanted them to be named. Just catchy. And everyone can go to these facilities. They are available to everyone free of cost. I mean, if you want to do research which can be published. So its procedure is almost similar how you apply for funding. So you write a proposal, you submit that proposal, and in that proposal you have to tell how this field is really at cutting edge, because these are very, very expensive, and very few facilities are there in the world. And you also have to say that why it cannot be studied with other, say, methods. For example, say electron diffraction, TM or XRD, or maybe any other tool, or synchrotron. So you have to justify that. So then they will send it for review, similar to how we do for funding proposal or for even our publications. And once review, give their comments, and then you have, maybe you'll get beam time, maybe you'll not get beam time. But it's open competition for everyone around the world. Anywhere you can apply. Maybe on the last day, I can introduce a method bit so that if anyone is interested, you can just apply by yourself. Okay. Oh, this is when I just want to show the instrument which I was mentioning that which I usually use, which is called Takumi, and it's called engineering materials diffractometer. So, but how it look like? So from the inside, it's maybe this big room, so it's enclosed in that. So neutron beam will be from this side, from one side, you have to get neutron. And for this specific instrument, you have 2 detector banks, which are usually have helium-3 filled in them. And then you can put anything in the middle. I mean, here it has a huge machine. You can change it, and you can do, say, thermomechanical processing. You can do diffraction experiments, and you can do a lot of things, which I will show different examples in the next tomorrow. Okay, I think now I will just repeat what I said, what I praised about neutrons. So I will just say that. Okay. First of all, neutrons have no charge, right? So what we can do with that? So it can be highly penetrating, and we can do non-destructive testing. So you can people do welding in situ, and then you can see how the structure is evolving. People can take their batteries, and they can see okay, how the batteries are charging and discharging. And you can use extreme environments. For example, you can I usually do experiments at ultra low temperatures, close to liquid helium. You can do at high temperature. You can do under higher pressure. You can apply magnetic field and so on. Then it has magnetic moment, so which is very good for magnetic properties, right? You can study magnons, you can study fluctuations, and so on. Then it has spin, so you can have polarized beam. You can have different atomic orientation, and you can, of course, coherent, incoherent scattering can also be done. Then their energies are similar to energies of elementary excitations, right? So you can have molecular vibrations, lattice modes, magnetic excitations. Then its wavelength is closer to, I mean, it have a range, but it's close to atomic spacing. So you can probe structure, right? You can probe structure, you can get information at a huge length scale, because with diffraction you usually get atomic spacing, atomic scale. But then with small angle neutron scattering, you can get close to tens of microns, right? So you can have a huge range of atomic information which you can gather from it. And as I mentioned, precise structure, of course, that's what we always want to look at. And it probe nuclei, right? It interact with nuclei, so then it can be sensitive to light elements, which we cannot do with other kind of techniques. It can distinguish between isotopes, right? And also, as I mentioned, that it can distinguish between adjacent elements in a periodic table, right? And just because now I'm just summarizing what I said. So you can see difference between X-rays and neutrons, that X-rays interact with electrons. while neutrons interact with the nucleus, and we know benefit of that. Of course, there are disadvantages, but advantages. And this, what I mentioned, that isotopes as well as light element detection and the distinction between adjacent elements. Okay, now we'll just show some radiographs and then we can finish. We are almost on time. Okay, so this is a radiograph camera. The one thing which I mentioned, that it's not always the case that you will get everything just by one technique. Sometimes you have to combine them. Some information you can get, say, for example, by electron microscopy, but some other information you can obtain from XRD, and some other maybe with neutrons. So here you can see with X-rays, you cannot see, it's like, for example, these inner components. But here you can see these like minor details of this camera. This is camera, right? These are bullets. This is with X-ray, this is with neutrons. So you can see this material, you can clearly see these granules inside by a neutron. This is radiographs, right? With neutron radiography, but with X-ray, no, it's like total like solid. Similarly, this is turbine blade. And people who work with, for example, Polar, they really love it. So you can see that with the X-rays, it's not these crystals, because we use single crystals for turbine, right? So we want, like, for example, look at their dimension, like how long or how thick they are, their dimensions, their features. So with neutrons, you can see it's clear, like you can see this structure, like within this kind of huge blade. And the difference is because of penetration power. Because with the XRD, you cannot go beyond few microns, but with the neutrons, you can probe really a millimeter, centimeter, in fact. Okay, this is the image which I really love. So you can see, you cannot, if you do XRD on this, you will not be able to see anything. This is lead, right? You will not be able to see anything. But with the neutron, so sometimes neutrons are transparent to heavy elements. We mentioned that they are very sensitive to light elements, but heavy elements will not interact with neutrons, so they can really pass through them. So this is lead, and you can see these lilies inside the lead cask, right? And when you do neutron radiography, you can see these. Isn't it amazing? Like if it's closed and you want to see, like, for example, with the archaeologists, like when they are excavating anything, and if something is like enclosed and they don't want to break it, maybe they can do this thing to, like, and people really do, a lot of archaeologists use neutron diffraction, neutron radiography for that purpose. But as I mentioned before, that you cannot get everything just by using one technique. Sometimes you have to combine. Some features you can reveal by using one method, and others you can do it by a different one. So you have to, like, optimize what you want to, which kind of information you want to get, and if you can get something new with this new technique, then that will be great. Okay, I think I will stop here. Yeah, quite on time. Okay, I think if anyone have any questions, so we can, like, maybe spend 10-15 minutes. If anyone have any questions, any comments, I want to see anything in the next lecture, so I would be more than happy to hear that. Okay, while you're thinking, I'll drink some water. Yes, please.
In your slide 2, you show trends between
And this one?
hydrogen and deuterium. What is the difference or the force between the deuterium and lithium of hydrogen and deuterium? Is there
Oh, you're saying, like, why they have different scattering cross section between hydrogen and deuterium. Okay. I see. So because this comes from the fundamental thing about neutrons, as we know that they interact with the nucleus. Hydrogen, how many neutrons hydrogen have? Nil, right? Deuterium, tritium, 2, right? So because they have different number of neutrons, so when the incoming neutron will interact with them, so they have different kind of binding energy. They have different kind of, so that's why when neutron will come, it will interact in a different way with them. But when we talk about, I mean, that's like just like basic way to understand it. But when you say like why they have some specific value for cross section, that we cannot answer because that's kind of fundamental properties for them. But we can understand because they're interacting with nucleus. So if you have one neutron, or if you have two, or you have none, then they will interact in a different way. So of course their scattering or their interaction will be a different. So that's why they have different cross section. Does that answer your question? Perfect. Please.
I have a question, maybe on topic.
Yeah. I love out of topic questions, by the way.
How do you stop the reaction at the installation source? It's like the source of sense, or how do you stop the reaction?
Okay.
It's out of topic.
Yeah, no. It's totally in the topic because they talked about Spolation source. So with Neutron, with the reactor, like you just submerge or like we insert boron control rods and we stop because we eat all the neutrons. But with the Spolation, so then we have to stop bombardment of these protons, these like very heavy. So you remember, like I shown this. Let me just go back. No, not this one. Okay, I forgot where it was, but because you have this. Oh yeah, it was in chip. Okay, here. So you have to send these protons from here and then this ring and then this ring. So if you cut off here, then of course there will be no proton to interact with the target because they have to travel all the way to reach the target. Of course, they have a number of like places where you can stop them. If you can switch off these magnets, because you have to excitate these new particles so that they can reach to target. So if you these magnets, like they have their power supply and everything. So if you switch them off, or if you stop their function, or if you stop that anti of those proton, your reaction will stop over there, right? Because it involves like so many steps. It's similar to like any kind of like equipment which we use. So we have to power supply, then this connection. For example, this like my computer is connected in this way, right? So if I like switch off that button, so of course I will not have power up to this level, right? So it's that way, like kind of like you have to stop that beam and it will not interact with the target. Clear? Perfect.
¿Una pregunta? ¿En español o en inglés?
Pues, en la educación de rayos X, nosotros, para el refinamiento de cristales, no sé si hay alguna diferencia en el refinamiento ahora con relación de neutrones.
How do you study grain refinement when you compare X-ray diffraction and neutron diffraction?
Grain refinement.
Yeah.
Okay. Okay. It can depend on, I mean, if you are talking about like if the grain size is reduced, how you can distinguish it?
Yeah, I think the question is about the method.
Or any crystals or rare crystals.
Okay. The question is about the material, when they are organic or inorganic.
So when the grain are growing like in that way? Okay.
No, but not growing, I think it's for grain refinement or any grain refinement.
Okay, I will try to answer like how I understand about question. So the thing is, we cannot see grains per se in outside the XRD. You have diffraction peaks. When you have very fine grain size, the peak will become broader, right? The second thing is about texture. One thing is about they become like they are very fine, so peak will broad. The other one is about texture. If you have, for example, grain, you do rolling or you go do compression or any kind of like method like that. So maybe your grain will be oriented towards, say, one specific direction, right? Then you will have more intensity for specific peak and less for the other one. For example, the single crystal, so you'll have just one peak, right, for that specific one. The same exact principle applies to neutrons, with one exception. I will show, like tomorrow we'll talk about engineering basic alloys, and I will show like what we exactly do in that. If you have fine grains, in neutrons you will have better statistics. Because when you have like neutrons, if you're using neutrons and your sample is thin, it will be difficult to, okay, I think I should go. It will be difficult because, as I said, neutrons are very, very slow compared to X-rays. So they have to accumulate certain accounts to come above, background level, and then to get a very good pattern. So if you have very fine grain size, you will get the same information how you get with XRD. Of course, people broaden in like they have because of fine grains, also texture is similar. But if you have like fine grain sample and a coarse grain sample, you will have better results with fine grain sample. Otherwise, everything else is same. Does that answer a little bit? Yeah. Okay, perfecto.
¿Alguna otra pregunta? Por favor.
Well, thank you. I have two questions. The first one, is it difficult to analyze boron steels in this technique?
Sorry, I could not.
Is it difficult to analyze boron steels
Well, oh, okay.
in this technique, or you can use? There is no difficult to analyze because you mentioned that boron absorbs neutrons. So
Yeah. Okay. So it depends how much boron we are talking about. How much boron? Give me a percentage. One weight percent, 0.1 weight percent, 10 weight percent. It depends.
low
Give-
boron steels with
Sorry?
part per million.
Oh no. Parts per million is okay because you have to see like we use usually thick samples for neutrons. So when we use, for example, say tensile samples, I think everyone understands that. So we usually use say thickness of like few millimeter, right? And then we have some width and gauge length. So usually we have a neutron beam of like 5 by 5, depending on like you can change it, but usually like we have 5 by 5 millimeter beam, which is very large beam. So if it's parts per million, it would not matter because it's like we have like really large area which we can cover. So when I said like it is difficult to study, that I was talking about like maybe like 1% is like you can forget about it. You will not be able to get much out of it. But it also depends like what is your source power. Spolation source, for example, if you go to Japan Proton Research Complex, and then you go to Australia, which have reactor based. So the same thing which you can do in that source at Japan or the one which in US, you cannot do that at source in say Australia because it's a neutron gain is low. So you have to have more neutron and you have to spend way more time. It also depends how thick is your sample. If you are saying like I want to like study say 0.5% boron, 8% boron in say 0.5 millimeter thick steel, that will be difficult. So parts per million, no issue. I mean, like we have like boron all the time, so that's okay.
Second question is it sensitive for analyzing residual stress?
Oh yeah, the one of the most popular thing which people does, especially metallurgists, that is analyzing residue stress neutrons. That is like you will see like so many like people actually really when they got out of weapon manufacturing, like creating a say fissile enriched uranium or something like that. The main thing which mostly mechanical engineers and metallurgical engineers were doing that was just studying residue stasis. They have done it. Chalk river was one of the most popular. Now it's like, I think, going to be decommissioned. But they did like residue stasis measurement for like 30, 40 years. And some of the most popular like people like in my field, like the same I think most people here, they are in residue stasis measurement. So of course that's that's the most important. You're welcome. Okay, that's it. Okay, last couple of minutes because I have to like prepare for next one, and which is at 5. So maybe a couple of more questions if you have, and then we can go for the next. Okay, no. Okay, then good. We can go. Perhaps. Okay, a very nice day, and hopefully see you maybe in seminar as well, and maybe in next time tomorrow, same time tomorrow. Okay, have a good day.